Anesthesia is used on a daily basis to provide the loss of feeling or sensation for basic medical procedures and as well as pain management. The loss of sensation or feeling is accomplished with or without the loss of consciousness. There are two classifications of anesthesia. One is general anesthesia and the other is local. General anesthesia requires a full loss of consciousness, while local anesthesia blocks the nerve endings. A sedative can be administered so the patient is unconscious during the procedure. Local anesthetic also works when the patient is conscious. Present-day anesthesia has come a long way from the 1800s. In the 1800s, there were three main anesthetics that were used: ether, chloroform, and nitrous oxide. Ether was used most commonly because it was considered safer as well as more effective than nitrous oxide and chloroform. The first successful operation that used anesthesia was in 1846 by William Morton. For the remainder of the presentation, we are going to focus on local anesthetics and their connections to topics in chemistry. All local anesthetics are organic compounds. Organic compounds contain many different elements, including hydrogen, nitrogen, oxygen, the halogens, as well as phosphorus, silicone, and sulfur. There are two main types of linkages that are found throughout local anesthetics. One is ester linkages, and the other is amide linkages. Ester linkages contain a carbon atom double bonded to an oxygen atom, and it is also linked with a single bond to an alkoxy group. An alkoxy group is an alkyl group singly bonded to an oxygen. This can be shown in written form as R-O. There are many different types of alkoxy groups. This picture shows many different types. Anesthesia that contains ester linkages are synthesized in the plasma of your blood. Different products that contain ester linkages include cocaine-procaine, also known as novocaine, benzocaine, and tetracaine. This picture shows the chemical structure of novocaine. Amide linkages contain a carbon atom double bonded to an oxygen atom, and it is singly bonded to a nitrogen. This picture looks at two different amide linkages that can be found in organic chemistry. Anesthetics with amide linkages are synthesized in the liver. Amide linkages have a longer time of action than anesthetics with ester linkages. Anesthetics with ester linkages include lidocaine, bupivacaine, and chloroprocaine. This picture looks at the chemical structure of the local anesthetic lidocaine. Lidocaine is used in many dental procedures and is also found in many numbing creams and gels. pH is an important factor in local anesthetics. What is pH and what does it stand for? Well, pH measures the acidity or alkalinity of a solution. pH stands for the power of hydrogen. pH has a scale of 0 to 14, with anything under 7 as an acid, and anything over 7 means that the solution is basic, with 7 being neutral. The pH of a solution affects the onset, as well as the duration of effect of anesthesia. The pH of local anesthetic is approximately 7.6 to 8.9, which means it is alkaline. This diagram shows a pH scale. As you can see, 7 is neutral. This means that anything above 7 is alkaline. With local anesthesia being in the range of 7.6 to 8.9, this means that most local anesthetics are alkaline. pH can be found mathematically by using the formula pH equals negative log times the concentration of hydronium ions. To find the concentration of hydronium ions, you must find the concentration of the ionized form of the anesthetic. there is a 1-to-1 ratio between the ionized form of the anesthetic and the concentration of hydronium. Anesthetic with more non-ionized portions have a faster onset. When the non-ionized portion breaks down, it makes ionized molecules as well as hydronium ions. When there is a smaller concentration of hydronium ions, the pH is higher. This explains why anesthetics have a higher pH, and the onset of the drug is faster. The addition of sodium bicarbonate causes the pH of the anesthetic to rise, resulting in a faster onset of the anesthetic. However, if the pH gets too high, a precipitate will form. The equilibrium of anesthesia. The relationship between ionized anesthetic, non-ionized anesthetic, and the pH are all part of the equilibrium of anesthetic. When the pH is decreased, the ionized portion of the anesthetic decreases, thus causing the equilibrium to shift to the ionized portion. This can be explained by Le Chatelier's principle. For example, when there is less of the ionized portion of lidocaine, the equilibrium shifts to the left of the equation. This causes the pH to gradually become larger.